So let's talk about radiation heat transfer. Energy can be emitted by any object in the form of electromagnetic waves or photons. So this is the physical reasoning behind having this sort of thermal energy transfer, which is in the form of electromagnetic waves or photons. So let's look at the spectrum, electromagnetic wave spectrum. If I make that. And let's say this is the wave, the micrometer, 0.1, 1, 10, 100. Now, here is what we have in terms of UV. This is a zone that we have visible. Here we have infrared. And from here, what we have is microwave. Visible is between 0.5 to 0.76 micrometer. That's the wavelength of that. The thermal energy radiations or thermal radiations generally happens between, this is thermal radiation, and that covers a bit of UV, visible and infrared type of a spectrum. Now, what's the magnitude of energy radiation from the matter? Suppose that we have a small object at a certain temperature. I'm just going to call it TS, and that's surrounded in a wide, much bigger surrounding that I'm going to call it T of surrounding. Now, an ideal thermal radiator, and I'll explain what do I mean. An ideal thermal radiator, or what we call black body, can emit energy to, depends on its surface temperature, sigma Ts to the power of 4. Now, sigma is 5.67 times 10 to the power minus 8 watt per meter square K to the power of 4, and that's Stefan Boltzmann constant. Ts is absolute surface temperature of the object that we are looking for, definitely in Kelvin, and EB, we call him as a black body energy radiations is the rate of energy radiation, which has a unit of watt per meter square. Now, in reality, the objects can only emit energy as a fraction of the amount that a black body can, or an ideal object can emit energy. So that's how we introduce a coefficient here called epsilon as emissivity. And when we deal with the real object, real object can emit energy, just using with a different color, as a fraction of what black body can emit energy, or epsilon sigma ts to the power of 4, where epsilon is between 0 and 1. This is the amount of energy that one object can emit. So let's say this is emitting energy. At the same time, this object can receive energy, radiation energy, from other objects or surrounding that is in the viewing point of that, or visible to that. Now, let's say we have, let's put it in this way, we have this object, and there is a unit. I'm just going to put it as 1, a unit radiation energy coming to an object. So this object can emit energy, depends on its surface temperature, and at the same time it can receive energy. Now the energy that comes to this object, part of that just gets reflected. So I'm just going to put this one, and we just show it with the fraction of that is getting reflected. A fraction of that is just getting absorbed. I'm just putting as an alpha, and a fraction of that is just passing through, just showing as a tau. Okay, so alpha is absorptivity, rho is reflectivity, and tau is transmissivity. Obviously, alpha plus rho plus tau is going to be 1. Now, what is important for us is the amount of energy that is getting absorbed to this object. So the amount of radiation energy that an object absorbs, if we show it with the G absorb, then this G absorb is going to be the fraction of what it's receiving here, and alpha is between 0 and 1, where G is incident radiation or irradiate radiation, which has a unit of watt per meter square. Or in another word, this is radiation energy coming to your object. Remember, we were just showing for a unit of this radiation energy coming to the object, and G's could be whatever number it has. And alpha portion of that is getting absorbed by the object. Now for each object, we are looking for the amount that is getting absorbed, net amount that is getting absorbed, and net amount that is getting emitted from that object, and that defines the radiation heat transfer. Now, the net rate or Qnet is emission minus irradiation, which is E minus S, or is going to be epsilon sigma A Ts to the power of 4 minus alpha sigma A T of coming from the other object, or let's say here is only surrounding, that is covering that area, to the power of 4. Now, assuming epsilon is equal alpha, which is not really the case, but for simplification, we make that assumption. We call our surface, we call the surface as a gray surface. So with that assumptions, this is going to be essentially the equation that we are going to use for the net radiations for an object. Q is going to be epsilon sigma A Ts to the power 4 minus T of surrounding to the power 4. Remember that here I was mentioning that we have a small object in a big surrounding, and that was because that I wanted to have 100% viewing, but viewing couldn't be really 100% like in many cases. So we define another factor as a view factor, or F. What it means is to take into account that not all radiation from one surface is seen by another surface. We will go more into the details of radiation later on.